All right, welcome to lecture 19 for ECE 203. Today we're gonna talk about a couple things. The first thing we're going to talk about is this general concept of how computing convolution in the time domain that corresponds to just multiplying things in the frequency domain. Okay, so we can kind of compute a convolution of two signals just by looking at their spectrum and multiplying them together. And so we're not going to spend a ton of time on this, but it's just kind of a good thing to know. Okay, so let's kind of remind ourselves what the frequency response of a filter was. So assume we have some filter H, and it's an LTI, or linear time invariant filter. Then the frequency response was basically the response that we got when we input a complex exponential at a digital frequency of f hat. Right? So we put in this sinusoidal signal at frequency, digital frequency f hat, and what we get out is another sinusoidal signal at digital frequency f hat, except scaled and phase shifted by some amount, and that amount is h of f hat. Right? That's the frequency response of the filter. So right away we can kind of just look at this for a while and realize that now, since the system is linear, if we input a sum of sinusoids, then what we get out should just be the same sum of sinusoids, but each one scaled by the response of the filter at that frequency. Right? So if we input the signal that's drawn there, okay, and that goes through the filter, then each one of these sinusoids gets affected by the green filter. I've just drawn a kind of a simple green filter that we've looked at before right there. And so each one of these sinusoids, depending on what frequency they're at, they get scaled, and the amount they get scaled and phase shifted by is given by the frequency response of the filter. Okay, so and just as kind of this general rule, we're seeing that the spectrum of the output signal, right, is just equal to the spectrum of the input signal, right, capital X of f hat, multiplied by the frequency response of the filter, h of f hat. Okay. So that tells us another way to compute the output of a filter, right? The first thing we saw was to compute convolution in the time domain. But what we're looking at here is, instead, if we just know the spectrum of X, and if we think of the filter response, the frequency response of the filter as the spectrum of the impulse response of the filter, then we can compute the output just by multiplying together those two spectrums. And then once we have that new spectrum of X of f multiplied by h of f, then we can go back, think of kind of undoing that spectrum to get back to the output time domain signal. All right. So the general underlying principle that people should think about here is that this idea of convolution in the time domain somehow equates to multiplication in frequency, right? And really what I'm writing here is another way to see that. If we take the spectrum of the output, right, which is x of n convolved with h of n, that should just be equal to, just using the logic we saw above, that should just be the spectrum of x multiplied by the spectrum of the filter. Okay, let's see this with a little bit more rigor and see how this is true even using the DFT. Okay, so let's take a step back and remind ourselves of the DFT expansion of a signal. Okay, so if we have a discrete time signal, little x of n, then we can always write that using its DFT expansion, right? And this was the equation for the inverse DFT, right? The IFFT in MATLAB. And so that equation was just the following. We summed over x of k, which were the DFT coefficients, and each one of those was weighted by a complex exponential, right? And that complex exponential was at a frequency, it's a signal at a frequency of, well, for k equals 0, it's at a frequency of 0 for k equals plus or minus 1 or n minus 1. It's a frequency of 1 over n, then 2 over n, and 3 over n, right? Remember the DFT we could think of as computing the Fourier series at the harmonic frequencies of 1 over n, at the harmonics of the digital frequency 1 over n. Okay, so the DFT writes just in a way to express any discrete time signal as the sum of sinusoidal signals. So when we're thinking about this, when we looked at the DFT before, we said it was for a finite length sequence, for a finite length discrete time signal. So it's also true for a periodic discrete time sequence, right? Remember, we could kind of interchange periodic and finite duration just by truncating. If we had a finite duration sequence, we could just turn that into a periodic sequence just by truncating them back to back. So let's think of a periodic a periodic discrete time signal x of n. Okay, so again I have the frequency response, which we saw on the last page written here. Input a complex exponential signal at a frequency f hat of f hat, and what you get out is another complex exponential at frequency f hat multiplied by the frequency response of the filter at that frequency, h of f hat. So what would happen if we input this signal x of n up here into the filter h? Well, let's just do that, right? So inputting any signal x of n into the filter h. But instead of thinking of it as just putting in this signal x of n, let's input its discrete Fourier transform expansion, okay? So we're going to input this equation that's at the top of the page. And why are we doing this? Well, again, right, because it breaks the signal x of n up into the sum of sinusoidal signals, sum of weighted complex exponentials. So then it's not hard to see that the output now is just a sum of, again, each term in this sum. Since it's linear, we can think of each term in this sum here going through individually, right? So what we get on the output, right, and each term in the sum, each one has a frequency complex, a frequency of f hat equal to k over n, right? So what we get out is just this same thing, x of k, that's just some complex number, multiplied by this sequence, the discrete time signal, e to the j 2 pi k over n times n, but now that's been scaled, right? It's been scaled by the filter. And how much did it get scaled by? Well, right, that's just the frequency response of the filter evaluated at the frequency k over n. Okay, so now I'm gonna kind of jump to the next line, and I'm just going to redefine the frequency response of the filter, right, evaluated at the frequency k over n. I'm going to just call that h of k, just kind of redefine that. Okay, and then what we get out is this expression that's written here. All right, so why did we kind of rename h of f hat evaluated at k over n? Well, if we come down and recall the definition for the frequency response of a filter, right? We can write that as this sum from L equals 0 to n minus 1, or however long the filter is. Let's say, assume that the filter is shorter than the period of the signal, okay? And then if it is, we're just going to add zeros to make it the same length. But then we could write the frequency response, right, as follows. And normally you just have in here you just have an f hat, right? But we're evaluating at f hat equals k over n, so that gets replaced by k over n. If you look at this for a while, you realize, wait a second, this definition, right, This is just the definition for the DFT coefficients. It's the definition of DFT, the DFT of the impulse response of H of n. Okay, so let's just call that H of k, and indeed that's the case. So what we end up on the output now is kind of two things we recognize, right? One, the DFT of x, then also the DFT of the impulse response h, okay? And then it's like we're combining those two signals, multiplying them together, and then this again, this and this part, right? That's would take the inverse DFT, right? That brings us back to the time domain. Okay, so this was a lot on one page. Let's jump to the next page and then try and take things apart a little bit further. So again, I have the same thing written on the top of the screen, right? We input a signal x of n, but conceptually we're thinking of the signal x of n as its DFT expansion, right? So that's what gets input. And then each one of those DFT coefficients now just gets scaled by the filter, right? And what we're left with at the output is now the multiplication of the DFT coefficients of x by the DFT coefficients of h, and then kind of that's the spectrum of the output, but then we have to go back to the time domain to get the time domain output, right? So the output y of n just be given here. So this tells us kind of another way to compute the output of an LTI filter, and that's the following. So step one, take the DFT of the signal, the discrete time signal x of n, and call that x of k. Then step two, take the DFT of the impulse response of the filter, call that h of k, and again we might need to zero pad that. And what I mean by that is if h of k is shorter than n, let's assume that it is, then we just add zeros to it, okay? And the third step is then just multiply now the DFT of x times the DFT of h. And then the last thing we need to do is take the inverse DFT to get back to the time domain, right? So we can think of this is taking the DFT of x, that gives us something in the frequency domain, right? Taking the DFT of h, then we find h, the frequency representation of h, then we multiply together the two frequency representations, and that's the frequency representation of our output. That's the spectrum of the output. And if we want to go back to the time domain, then the last step we have to do is take the inverse DFT. Okay, so kind of a conclusion from this, and something you'd see with a little more rigor in kind of further signal processing classes, is that convolution in time is the same as multiplication in frequency, okay? And one thing we can do to kind of see this concretely is if we take the convolution of two sequences in MATLAB, h and x, then roughly speaking that's the same as if you were to take the FFT of x, multiply it by the FFT of h, and then take the IFFT of the whole thing, okay? And the reason there's this kind of two squiggly lines, this approximation, that's since you really kind of need to zero pad, and also since in MATLAB the input x, right, when we compute a convolution, the input x, we're not assuming that it's not an infinite length thing that's periodic, right? It's a finite length thing. So right around the edges that can screw things up. In reality, you'd have to do a command called ccconv of h and x, and then you'd get the following thing with equality. But these are, for longer sequences, these are pretty much the same. And there's something called circular convolution, which we won't talk a ton about. But it's not a hard idea, and it's something you'd look at in detail in other signal processing classes. So I want to talk about really briefly what happens when we cascade filters together. And this is kind of another way to see that convolution in time is the same as multiplication in frequency. Okay, so if you guys remember, if we take two filters, right, and cascade them together, so take some signal x of n and pass it through h1, and then take that output and pass it through h2, the output that we get, right, is the convolution now between filter 1 convolved with filter 2 convolved with the input signal, right? And the way to remember that was the signal at this point, right, should be h1 of n convolved with x of n, and then we could use the associative property of convolution just to kind of reorder things, and then we could show that the output was then equivalent to if we just input the signal x of n into a filter with impulse response that was a convolution between h1 and h2, right? So the point being the output here and the output here are the same, right? And they're both given by this expression. Okay. So what happens to the spectrum of the output? Well, if we input, let's instead of thinking in terms of putting in a signal in the time domain, let's think of what happens. Think of the spectrum of that same signal, right? And now pass it through a filter H1 and then filter H2. Well, we know at this point, right, that the output here should be x of f, capital X of f, right? The spectrum of the signal times the frequency response of the filter. Okay? And so then that gets passed through filter H2. So then the total output that you get, right, is H1 times H2 times X. All right, pretty simple. So instead of having the convolution like we did in the time domain, if we think of what happens to the spectrums just get multiplied together. So that's actually the same as if we just think about what happens to a signal X, which has spectrum capital X of f, when that signal goes through a filter, right, with a frequency response of H1 of f times H2 of f. Okay? So to sum this all up, if we have a cascade of filters, H1 and H2, right, just two filters back to back, that's equivalent to a single filter with an impulse response of H1 convolved with H2, where H1 and H2 are the impulse responses of the individual filters, right? But then that's also equivalent to a single filter with frequency response H1 of f hat times H2 of f hat. So those filters are identical. It's just two different ways to characterize the filter. So what that tells us is that a filter with an impulse response H1 convolved with H2 has a frequency response H1 of f, capital H1 of f, times capital H2 of f. And again, that's just another way to see this general idea that convolution is, in time is equivalent to multiplication in frequency.